Warning! This video involves mains AC, which can cause serious injury or death. With that out of the way, meanwhile, I have two dysfunctional APC Smart UPS 750 units lying around now. And I don't need any more defect uninterruptible power supplies. What I really need is an isolation transformer. So basically something that I can plug into mains AC, here in Europe, in my country, 230 volts, and get out mains AC. The point is not mains AC, just AC, 230 volts. And the more power I can get through here, the better. So 500 watts would be quite nice. So why do I need an isolation transformer? Well, two reasons. First, I want to save my life when I'm working with mains AC. Second, I want to save my mains AC circuit and the optional oscilloscope I'm using to probe in that mains AC circuit. There are a lot of videos out on YouTube, EEV blog, how to not blow up your oscilloscope when measuring mains AC. And one building block in not blowing up your oscilloscope is an isolation transformer. And these things are expensive, and as I mentioned, I have two dead UPS units here. If you don't know what's in here, I made a detailed tear-down video of these APC Smart UPS 750s. Card link, so I won't show the disassembly in detail here. I will just go forth with it, and I promise we have some demonstrations how the isolation transformer can save me and my oscilloscope and my circuits as soon as it's finished. Yeah, that was obviously the unit from the teardown because all the parts are in here. Okay, I need to fumble about here a lot, and I don't want to do that around the camera, so you'll excuse when I stop the teardown here. As I said, there's an extensive teardown. Already there was a card and a link below. Okay, the teardown is done. I have basically here one chassis I want to keep, and I have two of these big transformers. And if you saw the teardown and the analysis of how that thing works, you know these transformers look something like that. So let's say you have here on the primary side a neutral tap, and then you have basically 1, 2, 3 live taps, which are middle voltage, middle tap, think 230 volts, and the upper and the lower tap are plus minus X% of the 230 volts. They are switched by relays just when you have a brownout, so you can basically boost the voltage a little bit. And on the secondary side there is some low voltage for the batteries to load, or the batteries to switched, supplied some EC here from the batteries to transform it up to the 230 volts you need to feed your devices. And I have two of them, and Now it's pretty evident what will happen. I mean, you just have to connect them, and yeah, voila. You have an isolation transformer. You not only have an isolation transformer, you have a double isolation transformer. So, but honestly, I have no idea how good these things are. Yeah, isolation-wise, they should be pretty good, but who knows? So, just on the safe side, yeah, use 2 of them. This has, of course, drawbacks. You have more losses because, yeah, first you're transforming down to some lower voltage, then you're transforming up. But due to the different tabs here, I think if I choose the right tabs, I can really even the losses out. So if 230 go in, 230 will go out. So let's do some measurements on such a babe here. First, let's check which is which on here. And, well, if this is according to German or European standards, blue should be neutral, and we should have here, oh, sorry, 5.4, 0.9, 0.7. Okay, so blue is not neutral, but neutral is on that side here. So let's have a go here. Yeah, 4.7, 5.0, and little higher, 5.4. So that reflects exactly, yeah, the primary side I've drawn here. So we measured from neutral to, yeah, I call it L1. So no, not 3-phase, just that we have 3 live connections from N to L1. 4.7, L2 5.0, L3 5.3 ohms, so 0.3 ohms difference. So our just the resistance of our primary windings looks like something like that, 4.7 ohms, and yeah, the smaller tabs at 0.3 ohms. Yeah, you could do some calculations now, how many plus minus X% from 230 volts up and down this is, but we will measure it anyway later. So let's continue measuring. And not to forget, I will mark the neutral side here, just for further reference and for avoiding catastrophes. Okay, what else should we measure? Am I hard in the ohms range? Yeah, obviously I'm hard in the ohms range. Come on. Not Siemens. Okay, standard range. Okay, my body. Because what I want to know now is, might we have some connection between the primary and the case? Because you remember, this is a used transformer, so out of a defect, yeah. And this is not really an isolation test, okay, because the test voltage is very low. But yeah, everything seems to be fine. We can try it again from the other side, but yeah, we know this is all very low. And yeah, our secondary should be, yeah, probably not even measurable here. Let me go back to continuity, which we'll have. Oh, it's actually not that bad. So anything between 0 and 0.2 ohms. So I don't, yeah, you need a milliohm meter to really measure that. But yeah, we have a connection here and also on that side just to be safe. Nope. Nothing to the case. So yeah, cursory isolation test, perfect. Now let's get dangerous and put some mains voltage in here. So I'm ready to put some mains AC here into that transformer, and yeah, when you work with mains AC, a good idea is to keep a clean bench. So, for example, remove all other cables from the bench. So, yeah, you don't plug accidentally something in that shouldn't be plugged in, and so forth. So, yeah, and yeah, my two-phase switch, so live and neutral here is offline. And I will switch it now and maybe we get a bang. But we don't get a bang. So, 237 volts and 12.6 volts. And I'm here, and you see plastic, I'm here in the L3, in the, yeah, longest winding. So, middle tap now, and I expect that voltage to be higher because, yeah, less windings on the primary, so the ratio between primary and secondary gets smaller, so higher voltage here. Let's see. Mains we have still 236 something, and output is now 14.2. And finally, the lowest tap. We are still 236 and 16.3. So I said in the beginning the isolation tests I did with just the ohmmeter here don't are an indication, but don't prove anything because these are really low voltage tests. What I now do is, yeah, this is on volts AC, and this buggers off to mains earth. And so I'm measuring basically, can I get a voltage between the secondary and mains earth when I power this up, which I will do now. And this looks considerable. Yeah, 30.6. Wow. At first glance, but we need to put a little load on that. Okay, shove the 1K resistor here in between, and let's try this again and watch the voltage if nothing explodes. Voltage gone. So, and a 1K load. And yeah, the final test, we measured the current that is actually flowing from secondary to mains earth on a short. Yeah, starting in the 10 amp range, just to be sure I'm not killing something. Power. And there is something displaying that could be interpreted as 10-20 milliamps, but it's not. 200 milliampere AC. Oh, now it's only 0.2 milliamps going down there, and then the 20 20 milliamp range, it's, oh, okay. So there's basically nothing happening, and it's safe to touch these or both of them. Okay, our transformer seems to be pretty okay. Just to be on the safe side, let's do that also with the with the core to main earth ground. And we have our 30, even more, 67 volts. And if I short that out, with a 1K resistor, it's gone. Yeah, you see, I'm quite confident that this thing is working by now. And yeah, let's try a 200 milliamp range, and there's nothing. 20 milliamp range, nothing. Okay, so this transformer seems to be fine. I will do now exactly the same with the other transformer, which is somewhere that direction. Then I'll come back to you. And one important note: this is not a valid isolation test for transformer by any norm or industry standard. That's a hobbyist method, and the equipment you create with that, or if I use that thing in some equipment, I can't touch it now. Don't even feel a buzz. The transformer is okay. But as I said, it's by no industry standard or norm really a test for transformer. You need to test for higher voltages, okay? And you need special test equipment to do that and to really actually read the isolation values in ohms, between the primary and secondary. I tested the other transformer too. That are the green values, and they are nearly identical. My mains AC has risen in the meanwhile by 2 volts. That's, it's 230 volts plus minus 10%. So everything seems to be in order. One digit, the least significant digit here, is off by 0.1 ohm on the primary, but okay. Design considerations at that point. I mean, obviously, I can run the secondary at 12.6 volts, 14.2 volts, or 16.3 volts, depending on which tab on the primary I use. You could say, okay, forget about it, but if you look at the current on the secondary for a given power, for 100 watts at 12.6, I need or will need to output 7.9 amps. At 14.2 volts, 7.0 amps. At 16.3 volts, 6.1 amps. It doesn't seem a lot, but if you go into the 500 watt columns, that's what the transformers up there somewhere at most should be able to handle. Upper limit 750 volt amperes, so 500 watts real power. This translates to 40 amperes, 35 amperes, and 31 amps. And that means if I go for the lowest tap here, and therefore for the highest secondary voltage, I need about 25% less current to pass in my low voltage circuit here. And that means I have 25% less losses, ohmic losses, in the secondary windings and in the wiring. So yeah, that's just a little design consideration I'm having for now. But yeah, let's build that circuit and fire it up. So input voltage from mains AC. Yeah, primary winding, secondary winding, going over to the other secondary, well now primary winding of the second transformer. So let's say the low voltage winding. I just have some flimsy cables here to do that. Yeah, better don't put any load on it. And then voltage on, yeah, I am in the voltage range on the secondary, well, high voltage side. Let's see what happens. And I have here 237 volts and I have here 267 volts. And yeah, you noticed I took the highest voltage tap out of my second transformer. So let me change that. So using the middle tap, I have 238 in and 234 out. And on the lowest tap with 237, yeah, let's say 238, I have 202 volts out. Okay, so the middle tap with 232 it will be. But then we haven't put any load on that thing. Now, what I'm also interested in is, yeah, with no load, what's the current flowing here in my in-between low voltage circuit? And there's a big surprise. A transformer is basically doing nothing, and I have here 2.8 amps, and yeah, the cable gets quite hot. And you see my output voltage, I'm on the middle tap again, is 243 volts. With, yeah, that other flimsy cable here in the loop on, yeah, the low voltage side, it was down to 232 volts. And that was just the loss in the cable from the, yeah, 2.8 amps that are flowing here. So yeah, and yeah, this is getting a little bit hot, so I will switch that off, and we need a better solution here. So I'm now in the yeah, highest winding, 239 volts, 307 out, and the middle winding, yeah, with good bridges, yeah, on the low voltage side, 271, and the lowest 236. It was 237 a while ago. But yeah, we're going down here on mains AC also. And yeah, this seems to be reasonable. So there is some loss, but yeah, usually the voltage around here is a little bit higher than the 230 volts. So yeah, we're finished. No, not yet. Next, before last, I wanna know how that whole thing behaves under load. Let's say a 100 watt light bulb. Here it comes. And we're here breaking down to 228 volts. At 238 volts, input voltage. So yeah, there are definitely losses here. Again, with no load, 235 volts. Oh, that's... just to be thorough, I now connecting the middle tabs at the input and output transformer. Maybe using more copper on the high voltage windings will change something. We'll see. And no, 228 doesn't change anything. Let's try the highest winding. 200, yeah, we are down to 237 and 226. So yeah, that really doesn't change anything. So yeah, that is not so fantastic. So basically, whatever tabs I used, I had a voltage drop of about-ish 7 volts for the 100 watt load. And for 500 watt, that would mean a voltage drop of 35 volts. And then I would be, with, what do we have here? Sorry, lights coming on again. 237 minus 35 is 202 volts, and that's below our minimum voltage here allowed for mains AC, which is 207 volts. So really drawing 500 watts out of here, the transformer would probably survive it, but it's pushing the limit voltage-wise on the output side. But 400 volts should be okay. So we'll stop that right here for now, and I will think about how we get these two transformers, and all the wiring into the case. And I will maybe augment the circuit diagram just a wee bit. Till then, bye.